Got it? All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the rain. Thank you for these students. I just pray that you'd be glorified, Lord, in what we do this day. In your name I pray, Lord Jesus. Amen. So I hope you don't mind the change in the due dates for the homework. I hope that's agreeable with everybody. Yeah. Indeed, it does.
Really? Yeah.
Yeah. Anything you guys missed, you can go back and fix.
It's a Christmas miracle. Almost.
It's like
a Halloween miracle.
it's like you're taking an online class.
Well, not really an online class. Sometimes we do that stuff too.
Oh, well, the ones I'm aware of.
Your wife's class, that class, stuff you all the way through the semester.
That's true, but I think you can keep working on the homework after it's due. Don't you? Are you sure you don't? I'm just saying, are you really sure you don't? Hint. Oh, it's already over. Oh, well, sorry, my advice to you is worthless. You got an A? You did not get an A. You earned an A. You received an A. Where did I put where on earth did I put the markers? Like, oh, duh. What's wrong with me? Good grief. Ay, ay, ay. All right, so calculus of the exponential and the log. So let me start at the beginning. Essentially, by definition, the derivative with respect to x of e to the x is equal to e to the x. Is there a question? All you guys are talking. Why are you talking? So that's the derivative of the exponential, right? Now, the next thing we'd like to figure out what is the... Oh, so let's do a couple of examples. So what if I have the derivative with respect to x of e to the 3x? How would that go? I do e to the 3x times the derivative with respect to x of 3x, which gives me 3 e to the 3x. Let's see here. How about something more exciting? E to the x squared plus 3. How's that go? So we again do the exponential x squared plus 3 because the derivative of the exponentials is the exponential again. Then I have to multiply by the derivative of the inside function. This is the chain rule, right? So this gives us what? This gives us 2x e to the x squared plus 3. I just like to write the factor out front for reasons of, I don't know, OCD. But let's see here. What else could we do? What if I had something like d dx of x squared e to the x? How would that go? Product rule. Very good. So we do derivative with respect to x of x squared times e to the x plus x squared times the derivative with respect to x of e to the x. But of course that is just what? That's just 2x e to the x plus x squared e to the x. Now, I would just like to emphasize that this can be simplified, and it's really not a bad habit to get into to simplify these. This would be 2x e to the x times what? 1 plus x or x plus 1? Yeah. I'll do 1 plus x just to keep with... Ooh, hold on a second. If I factored out the 2, what does that do here? Let me not factor... How about this? Let me not factor out the 2. All right? Is that okay? Let's not factor out the 2. Then what happens? 2 plus what? Plus x. Right now, you're like, well, how are you sure that's right? It's very simple. If we're right, when we multiply this out, we get back to where we started, right? If you can't multiply out your factoring, then you factored wrong. Now, who cares about this example? Well, here's an application. Like, why is simplification an important thing for some examples? So an application of that calculation I just did would be this. Find intervals on which f of x equals to x squared e to the x is increasing or decreasing, all right? So we just figured out what? We just figured out that f prime of x is equal to, what is it equal to? It's equal to x e to the x times 2 plus x, right? So we want to do what? In order to understand where it's increasing and decreasing, we want to draw a number line where we have the critical points. What are the critical points for this function? We do what? We set this equal to 0, and then we see what are the solutions to that. So what are the solutions to that? Yeah, x equals to 0 or x equals to minus 2, right? By the way, e to the x is not equal to 0 ever. So exponentials don't give you zeros, right? Good. So that means then I can just draw my number line. I've got my f prime of x right here, minus 2, 0, and then you just plug in some points, right? For example, if I plug in 1, it's positive. It flips signs between 0 and minus 2, and then it's positive over here. So apparently, f of x is increasing on minus infinity to minus 2, and from 0 to infinity, right? And f of x is decreasing on minus 2 to 0. So what can we could use the first derivative test to say more. What more could we say here with the work we've done? Concavity, we'll get to that in just a second. I like that, though. That's a good idea. We'll do that. Right, this is a local max, this is a local min, right? All right, so yeah, let's figure out what's the concavity of this function. How do we figure that out? How do you determine concavity?
Well, the negative is constant down. That's what that is.
Yeah, we got to do the second derivative is the thing.
But did you find that from knowing if it's from positive to negative, or is that just for?
Well,
You know, it's not from positive to negative.
no, I think I need the second derivative to figure out concavity for sure. I mean, it's definitely the case that I could give you a sign chart for f prime, and I could give you another sign chart for f prime prime, and like they could be inconsistent. This is a problem I've assigned in calculus 131 before. I give, here's a sign chart for f prime, here's a sign chart for f prime prime. Is this possible? But that's a little bit too mean for this class, so I didn't do that. But there is a link. What I'm trying to say is they're not completely disconnected, but I don't think you can read the concavity right off the first derivative yet, no. So we have to calculate f prime prime, but that's good. So one of the problems in your homework is like to calculate second derivatives of these things. So f prime prime of x would be what? It would be d dx of what? Of. Now, which formula should we use? This one or this one? I mean, what? I guess it doesn't matter. I'll stick with this one, though. And this gives me an excuse to use the triple product. Do you guys remember the triple product identity? Product rule, triple product rule, what is it? So let me call this thing F. Let me call this thing G. Let me call this thing H. The triple product rule says it's F prime GH plus F G prime H plus F GH prime. The way it works is you just write three things where you have the derivative on each one of the factors separately, but never more than once. That's product rule for three things. And so what do you get? You get f prime is just 1, right? So we get e to the x times 2 plus x e to the x times 2 plus x, because the derivative of e to the x is just e to the x. And then plus x e to the x times 1, right? The derivative of the last factor is just 1. Now, can we simplify this? Well, I suggest we factor out e to the x, right? Then what do I have? I've got 2 plus x. What do I get from the middle term? Plus 2x plus x squared. And then from this last term, I get yet another x. Now, I hadn't planned on looking at the concavity of this, so this may or may not work out nice, right? I'm just, freestyling. Let's see here. X squared plus, what is that? 4x plus what? Dose plus 2. Hey. Does that factor? Not that you guys see, but does it factor? Not with integers, perhaps, but if we complete the square here, that's x plus 2 quantity squared, right? Completing the square, I take half the middle term, add it to x, square it. Now, by doing that, what have I done? I've added 4, right? This is equal to x squared plus 4x plus 4. But I only have a 2 here, right? So I have to subtract 2 if I want these expressions to be equal. And from that, I can see that I have e to the x times x plus 2 minus the square root of 2 times x plus 2 plus the square root of 2. So it does factor, it's just not nice. You're like, what you've just done worries me. I don't know that. Well, that's fine. Maybe you know this. X squared plus 4x plus 2 equals to 0. How do we solve that equation? If you don't understand completing the square, if you started a new relationship, you don't have time for math, I don't know, whatever it is. Could be all kinds of things. I don't want math to damage your, your dating life or whatever. I mean, fine. I get it. Let's see here. Minus 4 plus or minus the square root of 16 minus 4 times a, which is 1, times c, which is 2, all divided by 2. So we get minus 4 plus or minus the square root of 8 over 2, which is minus 2 plus or minus square root of 2. Which, by the way, is the same thing you get from this. This has 0 when x is equal to minus 2 plus the square root of 2. And this gives you the solution x is equal to minus 2 minus the square root of 2. Those are the two possible points of concavity. In fact, those are, inflection points. Those are actually inflection points. ¿Es bueno? It's good? No? All right, I'm going to go on then. All right, so the focus of today's lecture, by the way, is much easier than this. This is just what we already did, right, with the new function e to the x, but it's increasing in concavity. We can still ask and answer those questions with our newfound friend, the exponential. The other thing we'd like to differentiate, though, is the logarithm, right? So how do you differentiate logarithms? What's the relation between the log and the exponential? So what I'd like to talk about now is what's the derivative of the natural log? So what's the fundamental relation is what? It's natural log of e to the x is equal to x, right? That's one thing we know. But what we really want to know is the derivative with respect to x of the natural log of x is equal to what? Well, since we don't know what it is, let's say that this thing is y. All right? So let's just, for the moment, let's figure it out. Let's say y is equal to ln of x. You with me? Let's give a name to the thing we want to differentiate. Let's call it y. Why not, right? Sorry for that. Not so sorry, though. I'll do it again. So then, since we don't know how to differentiate this, let's change it to something we do know how to differentiate. In other words, let's convert it to an equation about exponentials. In other words, take this lovely equation here and exponentiate it. That gives you e to the y, right? Is equal to e to the ln x, which is what? X, right. Now here I'm assuming that x is what? X is positive, all right? Now this is a great equation because I can differentiate both sides of this, right? What happens if I differentiate this? I get e to the y times what? If I differentiate with respect to x, I got to do the chain rule. I've got e to the y times dy dx by implicit differentiation. And on the other hand, on the other side, we get 1. See that? So I'm just differentiating. But what does that say? Let me get rid of these monstrosities before somebody asks me a question about it. I think there are some homework questions you have that are like tamer versions of this. So it's part of the reason I did that today. I wasn't just digressing. I was trying to help you with your homework. Believe it or not. All right. So then what? Solve for dy dx. That's, after all, what we're interested in. 1 over e to the y. But what is e to the y equal to? Go back up here. E to the y is equal to x. So this is 1 over x. And so what we've done through this little argument, standard argument, we have shown that the derivative with respect to x of the natural log of x is equal to 1 over x. This is how we differentiate the natural log function. Are we good? Should we look at examples of this now, maybe? Let's look at some examples of how to work with this formula. So what happens if I want to differentiate with respect to x the natural log of x squared plus 3? So I think of this as being the u, right? So what I have is d dx of the natural log of u. So the chain rule becomes 1 over u times du dx, right? So in short, we get 1 over x squared plus 3 times what? If this is u, what's du dx? 2x, yeah. So I usually like to write it 2x over x squared plus 3. You guys are caught up with me, I'll go on to the next example. Let's do something unpleasant. Well, slightly unpleasant. What if I had d dx of the natural log of the square root of, 3 minus x squared? Let's see here. If we follow the same chain of logic as over there, I would have 1 over the square root, right? times the derivative with respect to x of the square root function. Then what happens? This gives me what? 1 over 2 times the square root of 3 minus x squared, right? And then times the derivative of the inside function there. Chain rule again, right? It's a double chain. And so what do we get? We get, oh, check it out, square root and square root. Those simplify, don't they? We just have what? And the 2, and this, what does this become, by the way? This is what? This whole thing is just minus 2x, right? So if you look at this, you see some really neat cancellation, right? See the 2 here and the 2 here, they reduce, right? And this and that, they give us what? They give us just this. So what do we have? Let's draw it together here. We've got minus 2x. Oh, I can't follow my own advice. Minus x, right? I'll tell you what, I'm going to leave it, oh fine, minus x over 3 minus x squared. There you go. Now, is that the right way to do this example? You're like, if you're asking that question, the answer is categorically no, right? Yes, I know, but no, the answer is that is totally the wrong way to do this example. It's not incorrect, it's just not as lazy as we'd like to be, right? If you're a good student of math, you will be lazy. To be lazy is to be clever. The more clever you are, the more lazy you are. The optimal form of laziness, in an ethical sense, is just to know the answer and to write it down, right? I'm not talking about copying it from your neighbor. That's another thing altogether. Because statistically speaking, your neighbor's wrong, so that method will not work. You're like, I'll sit next to the person with 100 on their test. Like, well, anyway, let's not debate the best way to cheat. So a much better way to do this example would be what? Can anybody tell me? What should I have done? What would have been lazier in a good way? What did we talk about last class? Why did we talk about what we talked about last class? It must have been for some reason. Blank natural log of 3 minus x squared. Fill in the blank for me, would you? I mean, to make it more painfully obvious, this square root is 3 minus x squared to the 1/2. Yes, we can put a half right here. And halves are nice because halves are numbers, and you can take a half and you can just pull it out here by property of the derivative, right? And then all you got to do is take the derivative of the natural log of 3 minus x squared, which is ever so much easier, right? Because then you just got 1/2, 1 over 3 minus x squared, parentheses, times minus 2x. And there you go, back to where we got, with much more effort in the first run. Yep.
Why wouldn't you make it 1/2? I'm thinking divide it and subtract it and negative 1/2. Like when it was like 1/2, since it's 3 minus x squared to the 1/2, and then you take the derivative of that. Is it because it's
Oh, no. I did not take the derivative here. No. This step, going from here to here, that is just algebra. I'm using the property of logarithms, that the natural log of stuff to the p power is equal to p times the natural log of stuff. So that's what's at play there. Yes, sir.
So is it you always use the chain rule basically whenever you have like more than one number inside of the natural log?
Right. Well, I mean, this much is true. If we take the derivative with respect to x of the natural log of u, generically speaking, the pattern is 1 over u times du dx. So that's something we're always going to be using. Just like we're also always using d dx of e to the u is e to the u times du dx. These are the two chain rules we're using again and again and again and again and again in this section.
Okay, and the other thing is, you were able to pull that 1/2 out, you said. Why wouldn't you have just taken the derivative of that also and hit that 0? Why?
I mean, I suppose I could do the product rule. It just seems unnecessary.
Would it turn out the same way?
Yeah, of course. If you take the derivative with respect to x of cf, where c is a constant, you could say that's dc dx times f plus c times df dx. But of course, dc dx is by definition 0, so you're just left with what we usually call the homogeneity of the derivative that you can pull out a constant. But yeah, they are part of the same truth.
Yeah.
Mhm. Oh, okay, so let me show you another example, yeah? Suppose we wanted to differentiate with respect to x, the natural log of e to the x times the square root of x divided by x squared plus 42. Now, what would the wrong way to do this be? I don't want to do the wrong way, I just want to talk through it. The absolutely wrong way to do this would be to just apply the chain rule and then differentiate u, where u is the quotient of e to the x square root of x divided by x squared plus 42. This would be awful, right? You have to do the quotient rule, it's just nasty. The way we should attack such a problem is we should use the properties of logarithms, right, to simplify this. And so what are the properties of logarithms here? This is the same as the problem d dx of what? Natural log of e to the x plus 1/2 natural log of x minus the natural log of x squared plus 42. So let me call this Bob. So Bob is equal to this, all right? What else is Bob equal to? What's the natural log of e to the x? Do I need to differentiate that, or should I first simplify that? What can we simplify it to? It's not, well, kinda. The derivative will end up being 1. But before I differentiate, this is what? I can replace this with what? This is just, no, just x, right? Just x. Natural log of e to the x is just x.
Okay.
Now, you're right. When I differentiate that, that gives me 1. So when you told me 1, you might have been right. It depends on what you're thinking about.
Yeah, I was not thinking.
Oh, okay. Oh, okay. And then what's the derivative of 1/2 natural log of x? That's just 1 over 2x, right? And then we get minus 2x over x squared plus 42. And that wasn't so bad, was it? I mean, the problem looks awful at the start, but if you calmly apply the properties of logarithms that we talked about last class, these problems are not hard. If you try to do this without using properties of logarithms, they're very difficult. Agree? Would you like me to do it without? No, I'm not going to do it. I'm not going to do it. Not do it. All right. Now I want you guys, everybody here, try to do this derivative. The derivative with respect to x of x to the x squared plus 3. Can you guys calculate this derivative? What do you think, Megan? Can you do this one? Let's give you guys a minute to stew on that, and then I'll show you how to do it. By the way, this would be like number 11 in homework. I guess this is homework 12. I lost track. Yeah, this is like number 11 in homework 12, by the way. Let's see here. I would say the other ones we're doing are kind of like homework 12, number 7, 8, 9. I'm about to show you number 10 once we're done with this example. So, do you guys, anybody get it?
Well, I have a way that's probably wrong. Couldn't you just say x squared plus 3 times x?
I wish. Yeah, I mean, I wish we could do that, but the problem is it's kind of a combination of an exponential and a power function. So I can't use the chain rule for the exponential or the power function directly because it's neither one of those things. It's some kind of in between. Let me show you. So what you do, we're going to apply the same strategy we did to find the derivative of the natural log, right? That strategy is to give the name the thing you don't know how to differentiate. The thing you don't know how to differentiate, give it a name. Let's call it y. All right? Just let y equal that thing. And what do we have? We have an equation, right? We have that y is equal to x to the x squared plus 3. All right, I don't know how to differentiate that. But I do know properties of logarithms, right? So if I take the natural log of that, it gets me to something I can control. So the natural log of y is what? What's this? By the natural log of stuff to the p equals p natural log of stuff. The p here is, the power is x squared plus 3, right? So I can pull out x squared plus 3 times the natural log of x. So what do we have? We have found our way to the natural log of y equals to x squared plus 3 natural log of x. Do you see why we had to do that? Because we don't know how to differentiate other things. So I have to change it to something I know how to differentiate. I know how to differentiate natural log. I know how to differentiate x squared. And I can do implicit differentiation here to figure it out, right? So we differentiate implicitly. Was differentiate implicitly, what does that give us then? Differentiate implicitly with respect to x, what do we get?
1 over y dx.
Uh-huh.
And that's the product over there, right?
Right. So that would give us 2x ln of x, right? Plus x squared plus 3 times 1 over x. And then all you got to do is solve for dy dx, and you got it. But I don't like to leave my answer with a y in it. So just one more step, and then I'll be happy. d dx of x to the x squared plus 3 is equal to 2x ln of x plus x squared plus 3 over x, big parentheses, times x to the x squared plus 3. And there you go. That's how you differentiate weird stuff like this. Now, the only natural domain for functions like this is calculus tests. You won't find them much anywhere else. But since, in fact, a calculus test is part of your real life, this is, in fact, a real-world application for you, right? If you deny that this is a real-world application, you're denying your own existence. And I would encourage you not to do that. It's not healthy. Descartes was not so smart. He's kind of a dummy. Do I exist? Well, you're asking the question, you moron. Sorry. Not a philosopher. Sorry. Now, you see your answer that you were doing wrongly in here, right? Like, either you're probably going to say something like this, which is essentially, I mean, I don't know. It's you can kind of see aspects of whatever wrong answer you were writing down. They're probably in here, but this is actually the honest-to-goodness thing. This technique we just did is what's known as logarithmic differentiation. Logarithmic differentiation is basically, you say, okay, people ask me to differentiate something, and then you say, I don't like it. I don't want to differentiate something. I'm going to take the natural log of that something, differentiate that, and work back. This is logarithmic differentiation. I'll give you a story from my own life. I was taking a 300 level physics class. I don't know, these classes take something like 10 to 30 hours a week to do the homework, something like that. I don't know. It is a lot of time. I mean, they're kind of difficult classes. Anyway, I was sitting here and I come to this differentiation of this thing, and I was working with my friend Somber Paul, and not to be confused with Crazy Paul. Different Pauls altogether. There was a time where there was a splitting of the Pauls. It was a de facto divorce of my friends. It was truly horrible. I wasn't there for the divorce of the Pauls, but I remember well the semester I had to do separate visitation for both. It was really troubling. But anyway, they're good friends now. Actually, they don't talk. But it's true. Anyway, Somber Paul was sitting there doing homework with me, right? And I got to this derivative because there's derivatives. Junior level physics is wall-to-wall differentiation and integration. It's all of physics is calculus, all right, pretty much, or algebra, or some kind of conglomeration thereof. And I'm doing this homework problem. I'm just differentiating. I'm like, oh, all right, I'm getting there. And then Paul puts down his paper and he starts playing his guitar, starts working on whatever piece in Zeppelin he was working on at the time. And I'm like, what's the deal? Like, how did you finish that problem so quick? And he's like, I used logarithmic differentiation. And I was like, what's that? And then Paul said, oh. And then I said, oh. And then I learned what logarithmic differentiation is. I had to learn the hard way. I'm just telling you guys this for free. You don't have to live my life. You don't have to walk in my shoes. I'll just teach it to you now. So here it is. If you want to differentiate something like y1, y2, y3, y4, y5, yn. Suppose you want to differentiate product of n things. If you see something like this, you say, no, I will not do that. It's awful. Instead, you take this thing, you call it z or whatever you want to call it, give it your favorite name, and you say, well, the natural log of z is the natural log of y1 plus the natural log of y2 plus plus the natural log of yn. And of course, you can also use these kinds of properties if your y1s and y2s have square roots and other junk in them. The point is, you trade this product for this sum. Which do you want to differentiate, a product or a sum? I want to differentiate a sum. Sums are way easy to differentiate. And then you differentiate this, you get like 1 over z, dz, dx, and then, 1 over y1, y1 prime, plus plus 1 over yn prime, and then you solve for dz dx. This is the general pattern, okay? Done. This is logarithmic differentiation sketched. Now let me show you an example of it. The main idea here is that we can trade a product for a sum using the logarithm. So if I wanted, for example, differentiate y equals to, let's say, x squared times 1 over x minus 3 times e to the x cubed via log differentiation. How does that work? Let me draw the steps for you. So this is step number 1 is step number 0 is to give a name to the thing you're differentiating. I kind of already did that for us. I called it y. All right. Step number 2, or step number 1 really, is then to take the natural log of what you're given. So step number 1 here, natural log of y is equal to the natural log of this, right? So how do we simplify the natural log of a product of three things? What's that look like? We have to use the properties of logs, which is what? Natural log of x squared minus the natural log of x minus 3 plus x cubed. Where did the x cubed come from? What happened to the exponential? What was the in-between step I didn't write down? I'll tell you now, though. I went from this, went to the natural log of e to the x cubed, which goes to that. Hey, we don't need the triple product identity anymore, do we? See, I don't need to know the triple product identity to differentiate this because I can take the natural log and just differentiate a sum. See the difference? There is a cost. The cost is you have to know your properties of logarithms and use them correctly. If you don't, you can't do this method, right? But you need to do this method. It's part of the course. All right, so then I differentiate. Are you guys with me? So what happens if we differentiate with respect to x? We differentiate implicitly, right? We get 1 over y dy dx equals to what? Well, oh, hey, I'm not being as lazy as I could be. What could I have done before I differentiate? Don't let me get away with this, guys. Can we simplify anything there further? How about this 2? Yeah, let's put that 2 outside where it belongs. There we go. Now, I would still count you right. If I asked you to do logarithmic differentiation and you didn't pull the 2 out, but you did otherwise the general spirit of what we're doing, I would not take off points. Just for your informational purposes. But anyway, that gives us 2 over x minus 1 over x minus 3 plus 3x squared. You see, all I did was I differentiated this right here, right? Do you see that? Now all I have to do is solve for dy dx. That is, after all, what our goal is to calculate dy dx, right? So then dy dx is equal to x squared 1 over x minus 3 e to the x cubed times 2 over x minus 1 over x minus 3 plus 3x. Excuse me. Goodness gracious. I don't think this example is anything to sneeze at, though. Don't take it the wrong way. Let's see here. So there it is. And when I say do not simplify on this problem, please listen to me and do not simplify. You could multiply that out, but that's... yes, this whole thing is the y, right? Yeah. I saved myself the aggravation of writing. I just skipped basically this step in this time. All right, well, hey, let's do one more of these logarithmic differentiations. Unless there's a question about something. I think in terms of differentiation of logs and exponentials, I think I've covered, at this point, I've shown you the standard bag of tricks. I think I just owe you another example about logarithmic differentiation. Let me do that, and then I'll take questions. So if we wanted to differentiate with respect to x, say, x squared plus 7 to the 10th power times the square root of, e to the x plus 2, all divided by, I don't know, 3x plus 7. You could, I would say, differentiate by log. Use logarithmic differentiation to calculate, okay? This derivative. So how do we do it? Step number 1, or step number 0 as I was calling it, give a label to the thing you're differentiating. Let's call it y. Right? This thing we're differentiating, let's call it y. So the next step then, of course, is to calculate the natural log of y, right? So calculate the natural log of x squared plus 7 to the 10th power times, and I'm going to rewrite this suspiciously as e to the x plus 2 to the what power? The 1/2 power, right? And divided by 3x plus 7. Okay, so properties of logarithm allow me to simplify that how? I'll start with 10, natural log of x squared plus 7, plus what? Plus 1/2, the natural log of e to the x plus 2, where did the 10 come from? Do you guys get that? From the exponent. Where'd the half come from? The exponent again. We're adding because they're products. Division gives us minus, right? So I get minus the natural log of 3x plus 7. That's about as simple as we can get. Remember that the natural log of a sum is unhappiness, so it can't be removed. Oh, sorry, it's kind of a bleak picture of mathematics. Oh well. Anyway, differentiate this implicitly with respect to x. What do you get? You get yourself a 1 over y. dy dx is equal to, this gives me 20x over x squared plus 7. The first term differentiates to that. What's the second term differentiate to? 1/2. Looks like I've got an e to the x over e to the x plus 2. Now, if you guys don't understand what I'm doing, let me just propose to you that another way to write the chain rule for the natural log is as follows. So you put du dx up on the top, and then you put u over here. This is, pragmatically speaking, guys, this is what I usually go to for a formula for the derivative of the natural log. I just differentiate the inside of the natural log, put it in the numerator, and then divide by the function which is being natural logged. So like here, the 10 was outside, right? So the derivative of x squared plus 7 was 2x. 2x times 10 was 20x. And then I divide by x squared. Over here, I kept the half outside. I do derivative of the inside function, which is e to the x, and then divide by e to the x plus 2. This is this chain rule. One more term. What do we got for the last one? Yeah, minus 3 over 3x plus 7, right? Therefore, dy dx is equal to x squared plus 7 to the 10th power square root of e to the x plus 2 divided by 3x plus 7 times parentheses 20x over x squared plus 7 plus 1/2 e to the x over e to the x plus 2 minus 3 over 3x plus 7 rather. And there you have it. Now sometimes, because I'm such a nice guy, in the instructions to such a problem, I will write a little caveat. I will say, by the way, you can leave your answer in terms of y, if you like. Now, why would that be nice? Yeah, right. I can, instead of writing this, bleh, I can just write y here. And so that makes the problem a little bit easier in terms of the writing. And I figure if you can write that, you actually understand what's going on. Whether or not you can re-express that as x or not is somewhat immaterial to me. So I think if you look at old tests, you'll find that I did that. Or I meant to do it. I haven't looked back yet. I don't know. I am a creature of habit, though, so it is likely. Well, that's about it for this. Do you have any questions? E to the what?
1 over 9x.
Oh, 1 over 9x?
Yeah.
Oh, sure. Yeah, I have not done anything quite like that today. So let's call this thing u, right? We have d to the dx of e to the u. And so that will be e to the u times du dx. But that's e to the 1 over 9x times the derivative with respect to x of 1 over 9x, right? Which is going to give me minus 1 over 9x squared times e to the 1 over 9x.
Okay.
Good question. I did not do anything quite like that. Hey, here's another one. Check this out. What if you were asked to differentiate x over e to the x? You know how I'd do that? If I was given this question, I'd say, I don't like that question. I'm going to change it to this question instead. Because I like that more. Right? Because, I don't know, I personally am a big fan of the product rule. Not such a fan of the quotient rule. So if I do this, that's identically equal to that, right? And so I can just differentiate. It's e to the minus x e to the minus x. Where'd the minus come from on the second term? If we differentiate e to the minus x, what do we get? What's the derivative of minus x? What's the slope of the line y equals minus x? -1 everywhere. So its derivative is minus 1. Yeah. So this is just minus 1, and so we get minus e to the minus x, right? And that, folks, is where this minus came from, up here. So I did the product rule. I did derivative of x, which is just 1, times e to the minus x, plus x times the derivative of e to the minus x, right? Which is just minus 1, so I pull out a minus. Let me write that calculation again, but in full gory detail. If we have a minute, we can do it. We have several minutes, actually. So here. So d dx. Let's try this again, but more linearly, the presentation. So this is dx dx, e to the minus x plus x times d dx of e to the minus x. And so what this gives us is e to the minus x plus x e to the minus x ddx of minus x by the chain rule, which finally gives us e to the minus x e to the minus x, which is what I just said over here. My point is just that the logic of this equality here is that. Mm-hmm. Other questions? Well, I'll tell you what. I'll let you guys go. You go work on your homework. Come back Thursday. We'll see if you have questions then. And Thursday, we'll probably dive straight into what's known as anti-differentiation, which is the start of integration, which is kind of a whole other thing, as you shall see. Thanks, guys. You go ahead and hit. Yeah. Thank you.